Hello everyone, welcome to this video. In this video we shall be seeing question from December 2016 of CSIR-UGC NET and which is of 4.75 marks. They are asking which of the following are the characteristic numbers and the corresponding eigenfunctions for the Fredholm integral equation whose kernel is given to be this. That means they are asking characteristic numbers are basically the eigenvalues, right, and the eigenfunctions of the given equation. So our equation, they have given it to be Fredholm homogeneous equation, right? So our interval is from 0 to 1. Therefore our equation would something be like, if our unknown is gx, so we can write it as lambda integration from 0 to 1 between the interval, then kernel gt dt. Now we can split this interval 0 to 1 as 0 to x and x to 1. We can do that, right? X lying between 0 to 1. Because our kernel is given to be a step function or the piecewise function, right? So in the interval 0 to x, we have the variable t. So t is strictly less than or equal to x. So when t is less than or equal to x, that means we are talking about this function. So we'll substitute this value over here. Similarly, in the other case where t is greater than x, so t is greater than x, that means the first case, so we'll put x plus 1 into t over here. So our g of x becomes this, right? Now, in order to solve this, what we do is we convert this integral equation into the corresponding differential equation. For that, we will differentiate it with respect to x and we'll apply the Leibniz rule. What is that? That means in the left hand side, we simply derivate g of x, that would be g dash x, and the right hand side, we apply the Leibniz rule, lambda as such, integration from 0 to x, then the partial derivative of this thing, the first term, with respect to x, so that will give us t plus 1 into gt dt, this term. Then the derivative of upper limit with respect to x, so that would be 1, and substituting x in place of t. So lambda into 1 into x plus 1 into x into gx, that would be the second term, and third term would be the derivative of lower limit. What is lower limit? 0. So derivative of lower limit is 0. So this term is 0. Come to the second term, we'll do the same with it. Lambda as such, integration from x to 1, partial derivative of this whole term with respect to x, keeping t and everything else constant. So it would just be t gt dt because derivative of 1 would be 0. So we have lambda integration from x to 1 t gt dt plus the derivative of upper limit, that is 1 with respect to x. So derivative of constant is 0, so this whole term becomes 0, and minus of lambda as such, the derivative of lower limit, and lower limit is x, so its derivative would be 1, and then we have all these terms replacing t by the lower limit, that is x. So x plus 1, x and g of x. So now this terms cancels with this term, right, being same and of the opposite sign. So we are left with g of x as this. So mark this as equation number 2. Now because we have integral yet, right, so what we do is we again differentiate it with respect to x. We have g double dash x, and here we'll again have to apply the Leibniz rule. So lambda as such, right, integration 0 to x as such, and the derivative of this whole term with respect to x. Now you see there is no x, so the first term itself is 0, plus lambda into the derivative of upper limit, that is 1, and here replacing t with x, the upper limit. So it would be x plus 1 g of x, and minus the derivative of lower limit, and that is 0, right? Similar is the thing with the second term. Integration from x to 1, derivative of this with respect to x, there is no x, so it would simply be 0. Derivative of constant upper limit, that would be 0, and the derivative of lower limit, that would be lambda x dx. So our differential equation becomes g double dash x is equal to lambda g of x. In other words, we can write it as like this, right? Now in order to solve this differential equation, what do you need? You'll get two constants when you solve this. So therefore, you need two boundary conditions, right? So how do we get two boundary conditions? We'll look for g of 0, right? We'll look for g of 0, g dash of 0, g of 1 and g dash of 1. Why at 0 and 1? Because these are the end points, the intervals, right? 0 to 1 in which x belong. And we'll see what is the relation between these two. Do they form some equation? And these two. In some cases we get a relation in between these, and in other cases we'll get either this as constant or either this as constants. So when you get a combination of these two, you'll call them as mixed boundary conditions. And when you get only one of them, like this g of 0 as some constant, then you'll call it, or g of 1 is equal to constant, then you call it Dirichlet boundary condition. And when you only get this derivative as some constant, then you call it Newman boundary condition. When you get both, the combination of these, some multiplied by some constants, is equal to something, right? That is called mixed boundary condition. So let us see what do we obtain in this case. So we'll calculate g of 0. It comes out to be this, and g dash 0, g dash x is this. So when you put x is equal to 0, this integration is from 0 to 0, so this whole term becomes 0. And here lambda, integration from 0 to 1, here there is no x, so it comes as such. So now you see they both are equal. So that means you can write g of 0 is equal to g dash of 0, or you can write it as this. So we have mixed boundary condition for the left boundary point. So let us see for the second. G of 1 would be this. When you calculate it, when you put x is equal to 1 in equation number 1, and you'll get g dash 1 as this when you put 1 in this equation, right? Equation number 2. Again you see these two are equal, so we have the same condition at the right boundary also. So these are the boundary conditions, and this is our differential equation. Now depending on the value of lambda, we would have different eigenvalues and eigenvectors. So we'll take three cases: when lambda is 0, when lambda is positive, when lambda is negative. So when lambda is 0, this equation becomes g double dash x is equal to 0. So when you integrate this, you'll get g dash x is equal to some constant, or when you again integrate this, right, you'll get this. Now we need to determine what is the value of a and b. For that we'll use the two boundary conditions. So g of 0 minus g dash of 0 is equal to 0. This gives you b minus a, because what is g? G is ax plus b. When you put x 0, you will only get b. And what is g dash 0? It would only be a. So from here you get a is equal to b. Similarly, when you apply the second condition, you will get b as 0. So b is 0, that means a is also 0. That means the given function g of x becomes 0. So we are not looking for the 0 solution, the trivial solution, but we are looking for the non-trivial solution. That means the solution other than 0. So in this case we only get the trivial solution. So let us look at the case when lambda is positive. That say it is equal to k square. So our equation in that case becomes g double dash x minus k square g of x is equal to 0. So the corresponding auxiliary equation becomes m square minus k square is equal to 0. What is m? M is equal to plus minus k. Solving this, we get this. And for when m is distinct and real, in that case our solution is written like this. This comes from differential equations. We can take the derivative. The derivative would be this. right? Simple. Now, in order to evaluate A and B, we need two conditions. First is this one. When you put all the values, g of 0 would be 0 here, so you will get A plus B only. Similarly, g dash 0. So one is this relation and another is this relation, right? You can solve this, I guess. Now, in order to calculate the values of A and B, we can write these two equations as this is homogeneous system of linear equations. So the coefficient of A in the first equation, let us see this. The coefficient of A would be 1 minus k. So here it is. And the coefficient of B is 1 plus k. So here it is. Similarly, in the second equation, we have E minus ke. So the coefficient of A is E minus ke, and the coefficient of B is E raised to power minus 1 plus ke raised to power minus 1. So this is the second coefficient of B, right? So this is the system. Now, the only non-trivial solution for this system is when this determinant is equal to 0. You need to check this result in linear algebra, right? So now we'll calculate the determinant. So calculating the determinant and equating it to 0, you'll get k is equal to 1 or minus 1. These two conditions are only possible. If these two is the case, that means lambda is equal to k square, which is equal to 1 in both the cases. So when k is equal to 1, in that case our b becomes 0. When k is equal to 1 or minus 1, if you put it over here, you'll get b as 0 in this equation. So if you get b as 0, what is our a? Or the solution then becomes a into e to the power x, where a is arbitrary. Therefore, if we take the eigenvalue to be 1, lambda, which is equal to k square, right, which is equal to 1, right? So eigenvalue 1 corresponds to eigenfunction e to the power x. If you take a to be 1, so this is the eigenfunction. Therefore, option A is also correct. Let's see at our options. So option A, this is the correct option. Let us see at the third case, right? When lambda is negative, in that case, when lambda is negative, in that case, what do? We take lambda to be minus k square. So when lambda is minus k square, k is not equal to 0. In that case, our equation becomes g double dash x plus k square g of x is equal to 0. Or the corresponding auxiliary equation becomes m square plus k square is equal to 0. And m is equal to plus minus k, eta k. Now for this complex values, we have a solution like this. G of x is equal to a cos kx plus b sin kx, right? When we take its derivative, it becomes this, right? So now, in order to evaluate the value of constants a and b, what do we have to do? We have to apply this condition. We have to apply both the boundary conditions. When applying the first one, you will get a is equal to bk or a is equal to bk, right? And when you apply the second condition, we will get this condition, right? So again, we have two equations containing a and b, whose right hand side is 0. So we can write it as a system, this system of equations like this in matrix form, right? Again, in order to calculate the non-trivial solution, we should have the value of determinant as 0. So when you calculate the determinant, it would be sin k minus k cos k. And then you multiply these two with a negative sign, you'll get this. This term cancels with this term. So we are left eventually with this thing. So now two cases are there when k is equal to minus 1 or sin k is itself equal to 0. When k is equal to minus 1, we again reach at this case, which we have already discussed. So let us concentrate on this one. When sin k is equal to 0. So when sin k is equal to 0, this is only possible when sin k is equal to n pi, where n is plus minus 1 plus minus 2 and so on. Therefore k is equal to n pi with n is equal to plus minus 1 plus minus 2 and so on. Therefore what was our lambda? Lambda was minus k square, right? Lambda was minus k square. Therefore what is k? N pi, so it would be minus n square pi square. So this is our lambda. These are the eigenvalues or the characteristic numbers, right? And our solution g of x was a cos kx plus b sin kx, right? Now we already saw that a is bk, so where b is some arbitrary, because we can take any value for b. And what is k? K is n pi. So g of x then becomes, if we take b to be 1, because b can take any value, we can take particularly b as 1, right? So gx would become n pi, because k is n pi, cos n pi x plus b is 1 sin n pi x. So this is the thing where what is n? Plus minus 1 plus minus 2 and so on, right? So now we need to check for cases when n is equal to 1 or n is equal to 2. When n is equal to 1, it becomes, lambda becomes minus pi square, and the corresponding function when you replace n as 1, it would be pi cos pi x sin pi x. So this is the thing. And so this gives us option 4th as the correct option, minus pi square as the eigenvalue and pi cos pi x plus sin pi x, this as the eigenfunction. So this is also correct. So that means this is wrong. Option B is wrong. And for when you put n is equal to 2, you will get lambda is equal to minus 4 pi square. So that means g of x would be this. But here the eigenvalue is correct, but the eigenfunction is not correct. So this is not the correct option. So the only correct options are A and option D. Now this was the proper way to do this question, complete solution. But in question, if you are given these options, so you can go according to them. How you can do it? You can simply, when you have calculated your differential equation, then you simply take the value of lambda to be 1. In this case, you take the value of lambda to be minus pi square. In this case, you take value of lambda to be minus 4 pi square, and then solve to calculate the values of eigenfunctions. In that case, suppose at some point here doing the calculations, you have a doubt or confusion that which is the eigenfunction or is it correct or not. In that case, you'll be ruling out the wrong options and correcting, choosing the correct options. So in that way you can save time. But the general way to calculate all the eigenfunctions and all the eigenvalues, calculating it in a general way, so this is the method. I hope you understood it. So that is it for this video. Thank you for watching.